Bismillah ar-Rahman ar-Rahim. We have started talking about the rotational motion, and you have seen this relationship S equals R theta, where S is the distance traveled, okay, by a certain point on a rotating object, and this is R, how far is that point from the axis of rotation, and theta, or simply delta theta, which is the angular displacement. Okay, let me assume that I have object. This is my object, okay, and it is moving in a rotational motion. So I can show it this way. This is the axis of rotation, okay, and initially at time 0 it was located at theta initial. So this is my reference line initially, okay, and this is the axis of rotation. Okay, so my object is rotating about this axis of rotation. Okay, at a later time my object is rotating, and now it is at this angular position finally at a later time. Okay, so this is my delta theta. As you can see, all points of my object has moved this angular displacement, which is delta theta. Okay, let us assume it is 1 radian, for example. If it is 1 radian, all points, this point has moved 1 radian, that point has moved 1 radian, okay, and any point in between has traveled 1 radian. Okay, but if I would like to know how far did it travel, this point has traveled this much, which is, I call it S1 for this point, while the other point, which is at the end, has traveled that much, which is S2. As you can see here, which one is larger? S1 is closer to the axis of rotation, while S2 is further from the axis of rotation. So this point has traveled further distance than the point which is closer to the axis of rotation. Okay, so this is R1, okay, from here to there, this is R1, while R2 is greater. Okay, so this is R2. We can see here that S1 equals R1 delta theta, okay, and S2 is R2 same delta theta. Okay, so all points in my rotating object travel the same angular displacement, which is delta theta, but the points which are closer to the axis of rotation, this is the axis of rotation, okay, these points, their R is small. Okay, so their S, which is the distance traveled by them, will be smaller because they are closer to the axis of rotation. Okay, so from here it is very clear that S1 is greater than S2 for further points. And from here, my son, we are relating the linear quantity to the angular quantity. What is the linear quantity? Is the distance traveled. Okay, so S is the distance traveled by a certain point in my rotating object. Okay, what is the angular quantity? Is delta theta, which is the angular displacement. Okay, and this is the relationship between the linear quantity and the angular quantity. Nice. Usually I like to write this one as delta theta, okay, because it is angular displacement. It is not just the displacement. Okay, let us go one step further. As we have done before, and also shown in other examples, if we take the derivative of this equation number 1 here, okay, so if we take the derivative, so ds by dt equals R for certain points is the same, so this is R delta theta, so this will be d theta by dt. Okay, and here I am left with v, which is the linear velocity, that is equal to r, and we have seen this before, d theta by dt, which is omega. Okay, so here I have linear velocity equals r multiplied by omega. Let's see, how can we compare the omega for these points? Okay, I am talking about the same example. Okay, we have traveled, or my object has rotated, starting from this reference point to that final reference angular position. Okay, so delta theta is the same. Okay, and the time interval every point has traveled is the same. Okay, we have moved from here to there, let us say in 1 second. So this point has traveled this delta theta in 1 second, and this has traveled the same delta theta in the same time. So this means that omega will be the same. Okay, because my object is covering the same angular displacement at the same time. Okay, so omega is the same for all points. Okay, but r is different. Okay, so this point has the same omega as that point. Omega here is the same as omega there, the same as omega here, etc. Because we are covering the same angular displacement at the same time. So omega is the same. But r is different. This point has a small r, while that point has larger r. Okay, so how can we compare v1 here, v1 for this point, point number 1 and point number 2. So v1 will be r1 multiplied by omega, but v2 is equal to r2, and r2 is larger, and it will be the same omega. From here we can conclude that v2 is greater than v1. Okay, so the closer the point to the axis of rotation, its linear velocity will be smaller. As you go further and further from the axis of rotation, your r will be larger, okay, multiplied by the fixed omega for your rotating object. As a result, you will have larger and larger v. Of course, omega 1 is the same as omega 2, which is omega. And this is the beauty of angular motion. For angular motion, the angular quantity is the same for all points. Delta theta will be the same for all points. Omega will be the same for all points. Okay? Let us take one step further and take the derivative of this equation number 2. Okay, let me rewrite this one. Okay, number 3, I'll take the derivative of equation number 2. So I would like to go dv by dt equals r d omega by dt. What is dv by dt from linear motion or translational motion, which we have seen in the previous chapters? This is nothing but a, the linear acceleration, okay? And that is equal to r multiplied by d omega by dt, and you have seen this at the beginning of this chapter. This is nothing but alpha. Okay, so we say that the linear acceleration equals r, how far is your point from the axis of rotation, multiplied by alpha, which is the angular acceleration. Okay, let me go back to our example. Okay, I have my object is rotating, but with a changing omega. Omega is not fixed. Okay, it is moving slowly, then it goes faster and faster. Okay, with time. So we have these objects. I have the same alpha for all points in my rotating object. The rotating object alpha will be the same for all points. Why? Because the change in omega is the same for all of them in the same period of time. Okay, so alpha is the same. What can we conclude for the acceleration? The acceleration here will be smaller for points closer to the axis of rotation. For points which are further from the axis of rotation, it will be having larger linear acceleration. So from here we can say that A1 equals R1 multiplied by alpha, and A2 equals R2 multiplied by alpha. Okay, A1 is the linear acceleration of this point, the first point, and A2 is for the second point in my object. As you can see, R1 is smaller than R2, so we can conclude that A2 is greater than A1. Okay, but alpha 1 equals alpha 2, which is the same for all rotating objects. Very nice. So we have very important three relationships. These three relationships, let me rewrite them here. I have S equals R delta theta, and I have V equals R alpha. Then I have A equals R omega, and this will be R alpha. I start with linear quantity at the left hand side. This is linear displacement, okay, covered by a rotating point in my object. This is V, linear velocity, and this is the linear acceleration, equals R, which is how far my point from the axis of rotation. Please don't say that this R is a radius. Forget about the radius now. This R is how far your point from the axis of rotation, and multiplied by angular quantity. Okay, here multiplied by angular displacement, angular velocity, and here angular acceleration. Okay, don't forget that in the previous chapters, we talked about something called centripetal acceleration. Okay, and the centripetal acceleration, we said it is responsible for the change in the direction of the velocity. You have an object moving in a circular motion, if you see it here. Okay, this object, even if it is moving with constant velocity, V is constant, okay? Speed, the magnitude of the velocity is constant, okay? So speed is constant, but the direction is changing. So because the direction is changing, we have what we call centripetal acceleration, okay? So centripetal acceleration is responsible for the change of the direction of the velocity, okay? How much is that centripetal acceleration? You remember this. A centripetal. By the way, our textbook in this topic, it calls it AR, radial acceleration. Same thing, huh? Because the acceleration is along the radius, okay? It is toward the center, okay? So please forgive me, I'll use this as AR, okay? Which is the same as AC, the centripetal acceleration, which we have discussed before. So AR equals V square over R, okay? And to distinguish between this linear acceleration and this radial acceleration, we call this one A tangential, because the direction of this acceleration is tangent to the path, okay? So this is AT for this point is here. For this point, A tangential will be like this, okay? So each point has different tangential acceleration depending on how far is that point from the axis of rotation, okay? So we have radial acceleration, and this is responsible for changing the direction of the velocity. Okay? So always it will be there. If you have an object in rotation or in circular motion, you should have the radial acceleration. It should be always there. Why? Because you have a change in the velocity. But what about this tangential acceleration? Tangential acceleration will be there only if you have a change in omega. Okay, if omega is changing, it means your object was rotating slowly. It was slowly, then it will go faster and faster. So omega is changing, increasing or decreasing. Here I have a change in the omega. I have a change in the omega, you will have alpha. And if you have alpha, you will have tangential acceleration. Okay, so I should write here, this is responsible for changing omega. Okay, and if you have a change in omega, you will have a change in V. Okay, so I hope this is clear for everybody. Okay, we have two types of acceleration. One of them is always there for the rotational motion, which is the radial acceleration. It is towards center. It has a magnitude of V square over R. Okay, the other type is the tangential acceleration. It is always tangent to the circular path, and it is responsible for the changing omega. So if you would like to find what is the resultant or the net acceleration of a certain point, for this point on my rotating object, this was my rotating object. Okay, interested in knowing what is the total acceleration of this point. Okay, it has tangential acceleration tangent to the circular path, and there is a radial acceleration which is toward the center. Okay, and these are always perpendicular to each other. So always a tangential is always perpendicular to a radial. Okay, always, because one of them is toward the center and the other is tangent to the circular path. I hope you got this concept of relating the linear and angular variables clearly. So here I can draw the tangential acceleration for this point number 2. So this is a radial, and this is the tangential acceleration. Similarly, for this point, this is a tangential, and this is the a radial, which is the same as a centripetal, which we have seen before. By the way, we can plug in here for V, I can plug R omega. So this will be R square, omega square divided by R. So I can rewrite it as AR can be written as R omega square. So which one or which point has larger AR, point which is closer to the axis of rotation, or the point which is further from the axis of rotation? We agreed that omega is the same for all points. Okay, but R for the closer point will be small, for the farther point will be large. So AR2 is greater than AR1. Okay, for the tangential acceleration, the same. Okay, A tangential for this point, because alpha will be the same here and there. Okay, R for the closer point is small, R for the further point is large. So A tangential for this point is greater than A tangential for this point. Okay, what is the resultant acceleration for any point? Let us assume here for this point, what is the resultant acceleration? We can use the addition of vectors. So I have these two vectors which are perpendicular to each other, A tangential, tangent to the circular path, and A radial, which is toward the center. They are perpendicular, and this is the resultant acceleration for this point. Okay, for this point, this will be the resultant, its resultant acceleration, and not necessarily that they will be the same. Okay, and from Pythagoras, we can say that this acceleration has a magnitude of square root of A tangential square plus AR square. By the way, one further point also. Here V and omega they have not necessarily the same direction. Okay? So this equation, that equation, or even the third one, they are not vector equations because we have different directions. So I have omega. Omega is along our thumb if we are moving counterclockwise. Okay, but for V will be also tangent to the path. So it is the same direction as the A tangential. Okay, so omega will be, V. V is here also tangential. So this is V. Okay, it is tangential to the circular path for this point, and for this point V will be here. Okay, it is also tangential to the circular path. But omega, we use the right hand rule. Okay, so if this is my object is rotating counterclockwise, okay, so I use the right hand rule, omega will be outward and it is positive. Okay, if my object is rotating clockwise, so with our thumb, omega will be in the plane. Thank you.